buat minggu, the angle here is we need to look at the one active pressure. Our tummy a little bit move forward because we just eat. So that is active case, and this one so and also the up to know
Kanan.
Dia cakap lepas semua. Oh.
Uish.
Oh. Oh, tak panggil lah.
Apa?
Tak habis sesi.
Dah je? Nak tu.
Hi guys, welcome to the National University of Malaysia, university that inspiring futures, nurturing possibilities. Today, I will bring you guys around UKM. Let's go! What are you waiting for? Come and join us.
Okey, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan selamat pagi. Hari ini kita akan sambung lagi dengan kita punya chapter.
Hi guys, welcome to the National University of Malaysia, university that inspiring futures, nurturing possibilities. Today, I will bring you guys around UKM. Let's go.
Kita akan teruskan lagi tentang dengan Mahmai. Kamu akan buat graduate untuk aggregate Polish Stone Value dan juga untuk CPR dari dan kita akan cover kita tengoklah video and then can start with satu lagi, kalau masih ada sesiapa yang tinggal namanya daripada ahli kumpulan, please let me know lah, boleh maklumkan kepada saya and then kita akan sebab sebenarnya jadual lama tu disediakan oleh juruteraan ni, kita punya lab lah. Tapi mungkin ada, because some of you already text me yesterday saying that the name is not there, so kalau ada sesiapa lagi yang tertinggal, please let me know and then kita akan masuk dalam mana-mana kumpulan yang masih ada, boleh masuk lagi lah. Okey, itu perkara kedua. And then perkara ketiga, tomorrow kita akan ada satu talk lah on the crash, walaupun benda ni taklah berkaitan sangat dengan subjek kita, dia suppose on transportation engineer ataupun road safety. Tapi saya nak semua join talk tu besok. I think around pukul 12 lah, pukul 12 sampai pukul 1:30, normally around 1 hour plus lah untuk seminar ni. So later on, biasanya talk ni akan ada 2 presenters. So saya nak nanti kamu tulislah report untuk setiap presenter tu between 1.5 to 2 pages lah untuk report. Nanti saya akan saya akan sediakan folder dekat UKM folder, nanti kamu akan upload lah, kamu punya assignment kat situ. So please saya minta semua hadir untuk seminar tu, sebab nanti saya boleh dapatkan senarai kedatangan tu daripada organizer lah, sebab because that one organizer tu buat folder tu just purposely untuk kita punya kelas lah. Sebab tu kalau tengok kat situ dia ada kata Malaysia Edu macam tu lah, so untuk kita punya kelas. So biasa at the end of the day, organizer akan bagi saya sekarang peserta akan see you on the other side. Boleh join apa semua, please let me know. Sebab cuma saya tanya semalam daripada wakil kelas, suppose kita tak ada apa-apa lah between pukul 12 sampai pukul 1:30 tu. Boleh ya? Alright. Kalau tak ada apa-apa, kan kita boleh sambung. Can we continue with our lesson with the group 5 first or group 6? I think either one lah. Okay, please. Tolong unmute tak dengar
Group 5 dulu doktor.
Boleh. Please proceed.
Saya first keluar. Boleh nampak
Boleh. Clear.
Ya, doktor ada masalah teknikal kejap. Okay. Assalamualaikum and very good morning to our lecturer and friends. Today we are from Group 5. We're presenting the capacity and level of service at signalized intersections. For my session, we will be discussing about the highway capacity method. So for introduction, we do this highway capacity method to determine the cycle length based on capacity, and the capacity of lane group is given by this equation. Ci is equal to Si times by Ji over C, where Ci is the capacity of lane group in vehicle per hour, Si is the saturation flow rate group, and Gi is the effective green lane for lane group I, and C is the cycle length.
Sekejap ya. Apa nama tu? PowerPoint ni tak next. Tak move to the next slide.
Oh, sorry.
Okay.
Ini dia gerak. Gerak.
Okay.
Okay, saya mula dari awal lah. So apa ni highway capacity method? We use this method to determine the cycle length based on capacity. So for the formula, Ci is equal to Si times by Ji over C, where Ci is the capacity of lane group in vehicle per hour. Si is the saturation flow rate group of approach. Gi is the effective green for lane group I, and C is the cycle length. Next, we have the formula V over C, or this is equivalent to Xi, which is the degree of saturation. The formula is V over Ci, where V is flow rate of the critical intersection. If the road geometry design and total cycle time are to be considered, critical volume to capacity Xc is applied instead of Xi. Value of Vc is only to be considered as overall intersection mainly taken from the lane that have the maximum flow for each signal phase. So meaning that if we consider geometry design and total cycle time, the value of Vc we take only at the highest flow rate of the intersection. So for the critical VC ratio is given by this equation. Xc is equal to summation of V over S Ci times by C over C minus L. And the ratio of flow to capacity degree saturation
Masih dekat introductory punya slide ni. Awak share screen ke share window tu? I think
share screen.
Share screen
Dia tak gerak lah. Kalau tak gerak saya bagi orang lain present je lah. Maksudnya saya suruh orang lain share screen.
Control
tak
kan? Boleh, no problem.
Okay. Saya tukar.
Alright. Group member, siapa boleh bantu? Share screen, buat slideshow bawah tu.
Seorang boleh ni tak? Share screen tak?
Mas buat ke macam mana?
Okay. Looks better.
Kita pergi dekat third slide.
Oh, siap animated lagi. Rugilah tak nampak tadi.
Tu lah.
Kan?
Okay, ni tadi if the road geometry design and total cycle time are to be considered, critical volume to capacity XC is applied instead. Value of V over C is only to be considered as overall intersection, mainly taken from the lane that have maximum flow for each signal phase. Meaning that here V over C for this equation we take from the most the highest number of flow rate in that particular intersection. So the critical V over C ratio is given by this equation. XC is equal to summation of V over S Ci times by C over C minus L, where C is equal to cycle length and L of the total lost time per cycle computed as sum of the lost time. So we use this equation to compute to estimate the preferable or recommended signal timing in intersection. Okay, next. This is an example of a question taken from the book. Given here, the problem is we have two phase A and B. The phase A given 550 vehicle per hour and phase B 600 vehicle per hour, and given peak hour factor is 0.95, L is 14. The value of saturation per lane for each phase is 1900. So we found that the information here for phase A, V is 550. This is V for A and V for B. L is 14. And saturation is S is 1900 vehicle per hour. Okay, next. So the first step is we have to find the value for the first phase, which is V over C for A. So we divide V divided by S, and given the peak hour factor from the question, we used it to find the value for V over C. Okay, next. We also find value for V over C for B as well. So next step, we need to sum the value for both value of V over C, and the value is here is 0.937. Next. Using the formula XC, we calculate and substitute the value that we have found earlier. So we found that cycle time is 55.9 seconds, which roughly around 60 seconds. So 60 seconds in this context means that for each green time, the adequate green time is 60 seconds for the intersection. Okay, that's all for my part. I will pass to my friend.
Any question from the floor? Semua faham? What's your friend trying to tell? Okay, continue.
Determination of left-turn treatment. Left-turn vehicles at signalless intersection can proceed under one of three signal conditions, which are permitted turning movement, protected turning movement, and protected or permissive turning movement. Determination of specific treatment at a location depends on the transportation jurisdiction. Highway Capacity Manual suggests guidelines for providing protected left-turn treatment. Next. Next. Permitted left-turn movement are those made within gaps of an opposing traffic stream or through a conflicting pedestrian flow. The suitable of the permitted left turn depends on the geometric characteristic of the intersection, the turning volume, and the opposing volume. For example, when a right turn is made while pedestrians are crossing a conflicting crosswalk, the right turn is a permitted turning movement. Similarly, when a left turn is made between two consecutive vehicles of the opposing traffic stream, the left turn is a permitted turn. Next. protected turns movement. Others turns protected from any conflict with vehicles in an opposing stream or pedestrian on a conflicting crosswalk. A permitted turn takes more time than a similar protected turn and will use more of a available gain time. When a protected left turn phase is provided, an exclusive left turn lane must be provided. The length of the storage lane should be adequate for the turning volume so that the safety or capacity of the approach is not negatively affected. Length of the left turn lane can be determined from figure 8.13 and table 8.4. Table 8.4 shows the left turn bay length adjustment factors. Next. Figures 8.13. The values obtained from this figure are for a cycle length of 75 seconds and a ratio of 0.08. For other values, the length obtained from this figure is multiplied by a correction factor obtained from table 8.4. Next. Protected or permissive left turn movement is a combination of the protected or permissive conditions. Vehicles are first allowed to make left turn under protected conditions and then allowed to make left turns under the permissive conditions. Next. Highway Capacity Manual Guidelines for providing protected left turn treatment phase. It should be provided when two or more left turn lanes are on the approach. Also should be provided when the left turn and adjust volume is higher than 240 vehicles per hour. Should be provided when the cross product of the adjusted left turn and the opposing main line volume exceeds the value given in table 3.8. The opposing volume usually includes the right turn volume, unless the analyst is confident that the geometry of the intersection is such that the left turn vehicles can safely ignore the opposing right turn vehicles. A protected left turn phase should be provided if the left turn equivalent factor is 3.5 or higher. The left turn equivalent factor is used to convert left turning vehicles to equivalent straight through vehicles, because left turning vehicles generally require a longer green time than straight through vehicles. Next. This table 8.3 shows the minimum cross product values for recommending left turn protection. Next. Phase planes. The phase plane at a signalized intersection indicates the different phases and the sequential order in which they are implemented. It is essential that an appropriate phase plan be used at an intersection, as this facilitates the optimal use of the effective green time provided. The simplest phase plan is the two phase shown in figure 8.14. The higher the number of phases, the higher the total loss in cycle. It is therefore recommended that two-phase plan be used unless the traffic conditions at the intersection dictate otherwise. Figure 8.14 also shows example of other common phase plan. The dashed line indicate permitted turning movement and the solid line indicate protected movement. Next. And these are the figure 8.14 phase plans for permitted and actuated signals. That's all from me. Thank you.
Hello. Okay, good morning, Doctor and fellow friends. So today I'll explain on the delay at signalized intersections. I and Elamin actually will split this part and explain on half of it. Next, Soji. Okay, now speaking on the delay at the signalized intersection. Okay, one of the main objectives of installing a signal system at an intersection is to reduce the average delay of a vehicle at the intersection. For instance, when there's intersection like a junction, so they install the signal to reduce the average delay. So that's what we are studying about. Delay at signalized intersection is computed as the difference in the departure time and the arrival time of a vehicle. So they're explaining on the departure time when the vehicle leaves the signal and the vehicle arrives to the signal. It can also be said equal to the total extra time spent by the vehicle at the intersection that is required of the vehicle without the intersection of any hindrance. Next. Okay, the total delay time can be categorized into two different factors, which is the deceleration delay and the stopped delay. I'll explain on this next slide. So on the deceleration delay is the time loss that the vehicle takes in slowing down to reach to a stoppage in case the signal is red to a speed in case, or the second case is the queue when moving when the signal is green. For example, for instance, where there's car number 1, number 2, and number 3. So when the signal turns green, for the car 1 to react, it takes a certain amount of time for the car 1 to react. The second car will take lesser time, and the third car will take more lesser time, and the consequent car will be constant, the time for the reaction which they delay to move upon the signal turning green. The stop delay is the delay that the vehicle spend at the intersection while it is standing in a queue, while the car is waiting in a queue for the signal to turn green. Next, Ajay. Okay. Speaking on the delay, although most of the delay incurred at signalized intersection is directly caused by the traffic signal operation, a fraction or some of the delay due to the time required by the individual, which means the person himself, to react to the change of the signal display at the beginning of the green intervals, to mechanical constraint to individual driver behaviors. What the statement trying to say, it depends on the physical attributes of the driver himself of delaying his movement when the signal turns green. For example, when the headway of the departure vehicle are observed, it is seen that the front vehicle of the queue takes more time, as said earlier, to cross a stationary point than following the second vehicle to reach the saturation headway. The saturation headway is a point where when the first, second, third vehicle has successfully moved after delay and the following vehicle moves in a constant speed, that's known as the saturation headway after some time. Okay, moving on to the next slide, Alamin will take over the session.
Okay. In daily estimation models, to account for the additional delays due to delivery reaction time and vehicle acceleration constraint, the operation of signalized intersection usually defined in terms of effective signal interval instead of actual interval. Second one, the amount of difference between the actual and effective timing will thus depend on the assumption regarding driver reaction time at the beginning of the green interval and vehicle acceleration. Next. In order to estimation of delay, we can use expression developed by Webster, which is D equals C times A plus B over V times 100 minus B over 100, where D is average delay per vehicle, V is actual volume, lambda is proportion of cycle length, xg is degree of saturation, B is percentage correction. Next. The total hour delay of any approach can be estimated by determining the D for each line on that approach, multiplying each D by the corresponding lane volume and then summation of this value. The total intersection hour delay then can be determined by summation the total delay for each approach. Next. This figure shows the phase of intersection, which is consists of three phase. First one is two phase. Next one is three phase. Three phase also can be categorized into overlapping phase, and last one is four phase. Next. This is the A values table we will use in. They can be calculated from directly. The formula was that I mentioned in the first slide or taken from this table for A and B and correction value B. Next. So the A and B values depends, as you can see in the table, it depends on X, G value and lambda value. Next.
Next is cycle lengths of actuated traffic signals. Major disadvantage of fixed or pre-timed signals is that they cannot adjust themselves to handle fluctuating volumes. A vehicle-actuated signal is used when the fluctuation of traffic volumes warrants it. When such signal is used, vehicles arriving at intersection are registered by detectors which transmit this information to a controller. The controller then adjusts the phase lengths to meet the requirements of the prevailing traffic condition. Next. The following terms are associated with actuated signals. First, demand. The following terms are associated with actuated signals. First, demand, a request for the right of way by a traffic stream through the controller. Second, initial portion, the first portion of the green phase that an actuated controller is timed out for vehicles waiting between the detector and the stop line during the red phase. Third is minimum period, the shortest time that should be provided for a green interval during any traffic phase. Fourth, extendable portion, the portion of the green phase that follows the initial portion to allow for more vehicles arriving between the detector and the stop line during the green phase to go through the intersection. Fifth, extension limit, the maximum additional time that can be given to the extendable portion of a phase after actuation on another phase. Sixth is unit extension, the minimum time by which a green phase could be increased during the extendable portion after an actuation on that phase. However, the total extendable portion should not exceed the extension limit. Next. Next. Two types of signals, semi-actuated and fully actuated. Semi-actuated signals uses detectors only in the minor stream flow. It can be installed even when the minor stream volume does not satisfy the volume requirements for signalization. It is based on the ability of the controllers to vary the lengths of different phases to meet the demand on the minor approach. The signals are set as follows. The green signal on the major approach is preset for a minimum period, but it will stay on until the signal is actuated by a minor stream vehicle. If the green signal on the major approach has been on for a period equal to or greater than the preset minimum, the signal will change to red in response to the actuation of the minor stream vehicle. The green signal on the minor stream will then come on for at least a period equal to the preset minimum for the stream. This minimum is given an extendable green for each vehicle arriving up to a preset extension limit. The signal on the minor stream then changes to red, and that on the major stream changes to green. Next. Its operation requires certain times to be set for both the minor and major streams. For minor, times should be set for the initial portion, unit extension, maximum green and change intervals. For major, times should be set for the minimum green and change intervals. If pedestrian actuators are installed, it is also necessary to set a time for the pedestrian clearance. In general, the procedures described next can be used to obtain some indication of the required lengths of the different set times. First, unit extension. The unit extension depends on the average speed of the approaching vehicles and the distance between the detectors and the stop line. The unit extension should be at least the time it takes a vehicle moving at the average speed to travel from the location to the stop line. So this is the formula where U equal to average speed in kilometer per hour, X equal to distance between detectors and stop line in meter. However, if the desire is to provide a unit extension time that will also allow the vehicle to clear the intersection, Then we use unit extension time, where W equal to width of the cross street in meter and L equal to length of the vehicle in meter. Next. Second one is initial portion. This time should be adequate to allow vehicles waiting between the stop line and detector during the red phase to clear the intersection. This time depends on the number of vehicles waiting, the average headway, and the starting delay. The time for the initial portion can be obtained as in the figure, where H equal to average headway, N equal to number of vehicles waiting between the detectors and the stop line, K1 equal to starting delay. Third is minimum green. This is the sum of the initial portion and the unit extension. Next. Fully actuated signals. It is suitable for intersections at which large fluctuations of traffic volumes occur on all approaches during the day. Maximum and minimum green times are set for each approach. Its basic operation can be described using an intersection with 4 approaches and a 2-phase signal system. Next. The first is let phase A be assigned to the north-south direction and phase B to the east-west direction. If phase A is given the right of way, the green signal will stay on until the minimum green time ends, and an approaching vehicle in the east-west direction actuates one of the detectors for phase B. A demand for the right of way in the east-west is then registered. If there is no traffic in the north-south direction, the red signal will come on for phase A and the right of way will be given to vehicles in the east-west direction. That is, the green indicator will come on for phase B. This right of way will be held by phase B until at least the minimum green time expires. At the expiration of the minimum green time, the right of way will be given to the phase A. That is the north-south direction. Only if during the period of the minimum green, a demand is registered by an approaching vehicle in this direction. If no demand is registered in the north-south direction and vehicles continue to arrive in the east-west direction, the right of way will continue to be given to phase B until the maximum green is reached. At this time, the right of way is given to phase A and so on. A procedure similar to that described for semi-actuated signals may be used to determine the lengths of the different set times.
Nampak aku tu? Okay, move on to the next slide. The signal timing of arterial routes. Okay, arterial route is a high-capacity urban route that sits below freeway or motorways on the road hierarchy in terms of traffic flow and speed. In urban areas, the signal should be timed so that when a queue of vehicles is released by receiving the right of way, which is the green time, at an intersection, this vehicle should also have the right of way at the adjacent intersection. This coordination will reduce the delay experienced by vehicles on the arterial. To obtain this coordination, all intersections in the system must have the same cycle length. In rare instances, some intersections might have cycle length equal to twice the common cycle length. The common length is usually set with an offset that is suitable for Main Street. Traffic conditions at a given intersections are used to determine the appropriate phases of green, yellow, and red. The method used to achieve a required coordination, which is to reduce the delay experienced by vehicles on the arterial road, are simultaneous system, alternate system, and progressive system. The speed of progression are speed at which a platoon of vehicles released at an intersection will proceed along the arterial. So, first, the simultaneous system. All signals along a given arterial have the same cycle length and have the green phase showing at the same time. When given the right of way, all vehicles move at the same time along the arterial and stop at the nearest side signalized intersection when the right of way is given to the side streets. This is the equation that used to calculate the progression speed. Next, the alternate system. The intersections on the arterial are formed into group of one or more adjacent intersections. Signals are then set such that successive groups of signals are given the right of way alternately. There are two types of alternate system: the single alternate, in which when the groups are made of individual signals, and the double alternate, in which the group are made up of two adjacent signals. These are the equation used to calculate the progression speed for alternate system. An alternate system is the most effective when the intersections are at equal distance from each other. Move on to the next point. The progressive system. Progressive system provides for a continuous flow of traffic through all intersections under the system when traffic moves at the speed of progression. The same cycle length is used for all intersections, but the green indication for each succeeding intersection is offset by a given time from that of the preceding intersection, depending on first the distance from the preceding intersection, second, speed of progression for that section of the street, the limited or simple progressive system, when the offset and cycle length are fixed. The flexible progressive system is when the offset and cycle length can be changed to meet the demand of fluctuating traffic at different times of the day. Next, design of progressive signal system. The design involves the selection of best cycle length using the criterion that the speed of progression is approximately equal to the mean operating speed of vehicles on the arterial street. The equation is similar to the before, in which can be used to obtain the suitable cycle length by using the mean operating speed of the arterial. In addition, required cycle length for each intersection should be computed and compared to obtain cycle length found above. If the C value, which is the cycle length, is approximately equal to cycle for majority of intersection, it can be selected on a trial basis. However, it is usual practice to use cycle length that have been established for intersecting or adjacent system as guides for selecting a suitable cycle length. There is one in. Okay, move on to the example. Okay, move on to the example 8.8. Signals on an urban arterial are to be coordinated to facilitate the flow of traffic. The intersections are spaced at approximately 150-meter intervals, with at least one intersection being part of another coordinated system, whose cycle length is 60 seconds. Determine whether single, double, or triple alternate system is preferable for this arterial if the mean velocity on the arterial is 56 km/h. Okay, we can use the alternate system equation, which is the solution is, since there is one intersection in another coordinated system, it is necessary to use the cycle length at that intersection. That is c equals to 60 seconds. We also use the alternate system equation. So this is how to use the, okay, that's all from me. Okay, next, freeway ramp. Ramps are part of grade separated intersection where they serve as interconnecting roadway for traffic stream at different level and sometimes constructed between two parallel highways. To allow vehicles to change from one highway to the other. Divided into two groups, which are entrance ramp, allow the merging of vehicles into the freeway stream, and exit ramps allow vehicles to leave the freeway stream. Next. Next. This, as you can see, this is the figure for entrance and exit highway. Next. The freeway entrance control is essential to efficient operation of freeways when volumes are high. The main objective are to regulate the number of vehicles entering the freeway so that the volume is kept lower than the capacity of the freeways, also to reduce freeway crashes. Next. Next, Mas. Three methods of controlling freeway entrance, which are closure, local isolated metering controls, and system-wide coordinated metering control. Next. For the closure, usually using do not enter sign or by placing barrier at the entrance to the ramp. Three types of closure ramp, which are permanent, temporary, and time of day or scheduled ramp closure. Permanent ramp closure used when only necessary, for example, at location where severe safety problem exists and cannot be resolved by other effort. Temporary closure often used during maintenance or construction activities to avoid the potential conflict between ramps and construction vehicle. Also used to assist in the management of traffic in freeway near the location of a special event, and also depend on weather condition, time of day or schedule used during the morning and peak hour at location where recurring traffic congestion may lead to a severe safety problem. That's all from me. The other two will be explained by Nadira.
Hello. Okay. Next is local or isolated metering control. This method uses condition at a specific ramp to determine the metering rate. So the objective of this control is to improve the safety or alleviate congestion at the ramp. This metering method also can be used at two or more ramps on the freeway. And the effect of metering at one ramp is not coordinated with the effect at another. So next is system-wide or coordinated metering control. Here conditions are used that include those at other adjacent ramps to determine the metering rate.
This method can therefore use for ramps along freeway segment, an entire corridor, or several corridors where problem at one ramps may affect the other adjacent ramps. This control is effective than local control in dealing with capacity reduction that occurs as a result of road blockage and collision. Next. Next is for the ramp closure. It consists of two, which is barrier and enforcement personnel. Barrier consists of, it can be either manually placed or automated. So for manual barricade, it can be either portable or fixed. Portable can be moved from place to place, and it includes gates and cones. Next is for the fixed barricade. Fixed barricades are usually permanently installed and provide the flexibility of opening and closing of the ramp in response to traffic congestions. For the automated barricade, it is a fixed barricade that can be operated from a traffic management center, TMC, or from another remote locations. Next is for the enforcement personnel. It is another method of a ramp closure. So this method is usually used on a temporary basis when automated systems are either or not installed, or the maintenance personnel are not able to install the temporary barricades. That's all from me.
Bismillahirrahmanirrahim and Assalamualaikum everyone. So my name is Afza and I am going to continue with the last part of our presentation by explaining about methods of controlling the RAM meters. So before I go further, first of all, we need to know that RAM meters are one of our tools in freeway management. RAM meters are also traffic signals that install on freeway on ramps to control the frequency at which vehicles enter the flow of traffic on the freeway. RAM metering also reduces overall freeway congestion by managing the amount of traffic entering the freeway. So there are two methods of controlling the RAM meters. The first one is pre-timed metering and the secondly is traffic responsive metering. Next. So pre-timed metering are usually made for different times of the day and days of the week. Also can be used to reduce flow of traffic on the ramp from 1,200 vehicles per hour to 250 vehicles per hour. Also, a single entry system is used when rate is below 900 vehicles per hour, and a platoon entry system is used for rates higher than 900 vehicles per hour. Next. So this is the example of layout of pre-timed metering. Next. Aku yang lambat. Kenapa masih belum berubah ya? Okay. This is also the example. So as we can see at the start loop, the data collected such as speed and also other occupancy data from the main line. And at point 1 is where vehicles is pulled up to stop bar. And then at point 2, we can see there is the ramp meter and the vehicle stop when vehicle detected, signal turns green. And then the vehicles can merge onto the freeway. Next. Aduh. Okay, the second methods of controlling the RAM meter is traffic response metering. This method uses actual current information on traffic conditions from freeway loop detectors or other methods of metering. This method capable of responding to short-term changes in traffic conditions. The layout are quite similar to pre-time metering, but there are some additional features. And there are two methods can be used to determine metering rate. The first one is local traffic responsive, and the second one is system-wide traffic responsive. Next. I think that's it. Thank you. Oh, ada lagi tu. Oh. Aku tak nampak. Okay, so this is the comparison between pre-time and also traffic responsive. There are some similarities and also differences. For example, we can see that appropriate for localized problems are applied for both pre-time and traffic responsive. Also, detection in the field is not needed for pre-time, but detection in the field is needed for traffic responsive. And for system-wide, both are appropriate for widespread problems, but for pre-time, detection in the field is not needed, while in traffic responsive, detection in the field is needed. I think that's all from me. Sorry for any inconvenience. Thank you. Inconvenience. Thank you.
Okay, terima kasih Kepala Lima di atas pembentangan. Dr. Su, kita continue dengan next group ya.
Boleh, kita continue dulu.
Okay, sebab group 5 banyak sangat ada hiccup. Okay, kita continue lah dengan group 6 dulu.
Boleh nampak ke slide? Sekejap ya. Boleh. Okay. Assalamualaikum and good morning to everyone. We are group 6 and today we will be presenting about capacity and LOS signalized intersection. Okay, the highway capacity method is used to determine the cycle length based on the capacity of a lane group, and the saturation flow rate is the maximum flow rate on an approach or lane group when 100% effective green time is available. And also, the capacity of an approach or lane group depends on the percentage of the cycle length that is given to the approach or lane group. Okay, next we have the formula for the capacity of an approach or lane group, which is CI. And we also have the formula for the ratio of flow to capacity, which is V per C. Next, we have the formula for the critical VC ratio for the intersection, which is XC. If VC ratio is less than 1, the cycle length provided is adequate. Okay. Example 8.6, from this question, we can see we have 4 different flow ratios and we need to find number 1, the shortest cycle length that will avoid oversaturation. Number 2, the cycle length if the desired critical VC ratio is 0.95. And number 3, the critical VC ratio if a cycle length of 90 seconds is used. Okay, to solve number 1, we know the shortest cycle length that will avoid oversaturation is the cycle length corresponding to the critical ratio XC, which is equals to 1. And we need to find the C, which is cycle length.
So we can just use the formula that's been shown just now and solve this question. And same goes to number 2 and number 3. Next is example 8.7.
Okay, basically, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Boleh dengar ke?
Boleh.
Okay, so basically, example 8.7 is there's a few steps. Wait a minute. Alright, so the first step is we need to determine the summation V over S. So summation V over S, we calculate using all the critical length groups that given. And after that, we need to find the cycle length for XC. So basically, XC is equal, same with V over C, which is ratio flow capacity. So once we use XC is equal to 0.85, and then we substitute into the formula given based on the equation 8.15. And then we substitute, we got the C in second, which is 100 seconds. So after we find the cycle length, we need to find the minimum yellow interval. So also by using the equation given, substitute, and then we get the answer. And then the most important thing that here that we know which XC will be used. So if for this situation, we will use XC 0.85. And then we need to know, and then we need to determine the actual green for each phase, and which is G. Actual green is G. So allow a yellow interval for 5 seconds for each phase. So in this case, the total effective green time, which is G, CLR, in this case is R is equal to 0. So we substitute, and then we will get the minimum time required for each approach. So there is east, west, south, north. So we will make sure that we already calculated for each minimum time required. So because of the phasing system used, the total time available to cross each approach is east to west approach. Approach is 5 plus 25. Just now we already calculated below. And then the minimum time required are therefore satisfied. So basically, all of the calculation we need to, all of the calculation we have 4 stages. First is just now we need to find the XC, and then we need to find the C, and then we need to find the minimum yellow, which is tau minimum. And then we need to find what is the minimum time required for each approach, east, west, south, north. And then we also need to know that how to determine the determination of left turn treatment. So the left turn treatment is the vehicle at the signalized intersection, which is can proceed under 3 signals. So we need to choose between these 3 signals, which is permitted, protected, and next slide, Ufa. Okay, this one. Alright, so we need to determine with the within these three signal, permitted, protected, and protected permissive turning movement. So as the permitted, the turning movement are those who made between gaps of an opposing traffic stream through a conflicting pedestrian flow. So as for example, when a turn right is made while pedestrians are crossing a conflicting crosswalk, the right turn is a permitted turning movement. So the suitable of permitted turns at a given intersection is depends on the geometric characteristic actually of the intersection. So the turning volume and the opposing volume is considered lah. So protected turns are those turns protected from any conflict with vehicles in opposing stream and pedestrians of conflict crosswalk. So as the protected permissive, we combine. Okay. Permitted. Yes. Okay. As the permitted permissive combines the protected and permissive conditions, which is allow the car to make left turns first under the protected condition, and the second one is subsequently under the permissive condition. Hence, we need to next slide, Ofa. So hence, we need to determine the specific treatment at the location depends on the transportation jurisdiction. So the guidelines are vary from one jurisdiction to another. So based on the highway capacity method, however, they are suggested to follow a few guidelines. such as one is the protected left turn, second is protected left turn face should be provided when the left turn and adjusted volume is higher than 240 vehicle per hour. So the third one is the left turn equivalent factor is used to convert left turning vehicles to equivalent straight through vehicles, because left turning vehicles generally require a longer green time than the straight through vehicles. So a protected left turn face should be provided when two or more left turn lanes on the approach. The length of the storage lane should be adequate to store 11 half to 2 times of the average number of vehicles queues per cycle. So it is function. The function is of it is a function of several traffic parameters, including cycle length, signal facing, and arrival rate. So basically, the phase plan at a signalized intersection indicates the different phases used and the sequential order in which they are implemented. The higher or the number of phases, the higher the total loss time in the cycle, the L is actually. So it is essential that an appropriate phase plan be used at the intersection. So I guess that's all for me. Next. Yeah.
Okay. Go on to the next slide. Is about the delay at pre-time signalized intersections. Okay, the main objective of the signal timing is to reduce average delay of vehicles and reduce probability of crashes. Delay is an important measure of effectiveness to use in the evaluation of a signalized intersection. As you can see on the screen is the delay measures graph, and there are the D1, D2, and D3, where D1 is the stop time delay, D2 is the approach delay, and D3 is the travel time delay. Okay. Next. Okay. Go on to the next slide is about the delay diagram. As you can see, it illustrates a graph of a total vehicle vs time. The time axis is divided into periods of effective green and effective red. Vehicles are assumed to arrive at a uniform rate of flow. Okay. Uniform arrivals assume that the inter-vehicle arrival time between vehicles is a constant. Assuming no pre-existing queue, arriving vehicles depart instantaneously when the signal is green. When the red phase begins, vehicles begin to queue as none are being discharged. Thus, the departure curve is parallel to the x-axis during the red interval. When the next effective green begins, vehicles queue during the red interval depart from the intersection at a rate called saturation flow rate. For stable operations, depicted here, the departure curve catches up with the arrival curve before the next red interval begins. Next. Okay. Next is about the uniform delay. Okay. Uniform delay is based on an assumption of uniform arrivals and stable flow with no individual cycle failures. No signal cycle phase here means no vehicles are forced to wait for more than one green phase to be discharged. During every green phase, the departure function catches up with the arrival function. Total aggregate delay during this period is the total of all the triangular areas between the arrival and departure curves. This type of delay is known as uniform delay, where uniform vehicle arrival is assumed. Next. Okay, random delay. Random delay is an additional delay above and beyond uniform delay because flow is randomly distributed rather than uniform at isolated intersections. As you can see in the figure 4, it illustrates that some of the signal phases fail, where at the end of the second and third green intervals, some vehicles are not served. By the time
by the time the entire period ends. However, the departure function has caught up with the arrival function and there is no residual queue left unserved. This case represents a situation in which the overall period of analysis is stable. For these periods, there is a second component of delay in addition to uniform delay. It consists of the area between the arrival function and the dashed line, which represents the capacity of the intersection to discharge vehicles and has the slope C. Okay. Next. The next slide will be presented by Akasha.
This graph about overflow delays. Additional delay that occurs when the capacity of an individual phase or series of phases is less than the demand or arrival flow rate. The worst possible case, every green interval phase for a significant period of time, and the residual or unserved queue of vehicle continues to grow throughout the analysis period. In this case, the overflow delay component grows over time, quickly dwarfing the uniform delay component. The latter case illustrates an important practical operational characteristic. When demand exceeds capacity V over C more than 1.0, the delay depends upon the length of time that the condition exists. In figure 5, the condition exists for a long time and the delay continues to grow throughout the oversaturated period. This type of delay is referred to as overflow delay. Next. Delay at a signalized intersection can be expressed using below equation. Next. This figure about phase plans for pre-time and actual signals. Traffic signal facing reduce conflict between traffic movement at signalized intersection. A phase may involve one or more vehicular movements, one or more pedestrian crossing movements, a combination of vehicular and pedestrian movement. I will explain about the phase in the figure. For the first one, two phase. Each leg of the street with left-turn phase has its own phase. Each phase ends as soon as it's run out of traffic. This is also called split phasing. The next one, three phase. Exclusive left-turn phase. The lagging left turns are after the opposing through phase. Note that each through phase can end separately. Each one ends as soon as it runs out of traffic. The lagging green overlapping phase. The lagging left turn is before the opposing through phase. The lagging left turn is after the opposing through phase. Note that the lagging left turn phase must end before lagging left turn phase can begin. The last one for the fourth phase, two left turn phase. The lagging left turn is before the opposing through phase. The lagging left turn is after the opposing through phase. Either the lagging left turn or its parallel through phase can end first. Each one ends as soon as it's run out of traffic. That's all.
Assalamualaikum and good morning. So what is cycle length of actuated traffic signal? This type of signal is varied in according with the demand of traffic as registered by the actuation of vehicle or pedestrian detectors as one or more approaches. Actuated traffic signal capable of adjusting themselves. When vehicles arrive at intersection, signals were registered by detector, then transmitted to a controller. Phase length can be adjusted to meet the requirement of the prevailing traffic control condition. Can be either semi-actuated or fully actuated. Next slide, please. This is actually based on ATJ. Arahan Teknik Jalan 13/87, page 28. So the is stated there, advantage of traffic actuated signal. First, usually reduce delay if properly timed. Adaptable to short-term fluctuations. So the third one, usually increase capacity. The fourth, provide continuous operation under low volume condition as an added safety feature when pre-time signal should be put on flashing to prevent excessive delay. And the last one is especially effective at multiple phase intersection. Next slide is the disadvantages of traffic actuated signal. First is the cost of an actuated installation is 2 to 5 times the cost of pre-time signal installation. Second, actuated controller and detectors are much more complicated than pre-time controllers, increasing maintenance and inspection skills, requirements, and costs. Third, the detectors are costly to install and require careful inspection and maintenance to ensure proper operation. So based on the ATJ, there is more about a type of signal. The example is traffic adjust system, and they actually compare the pre-time and traffic actuated controls. So next slide. The terms, slide from terms. One more back. Okay, this term. So the first term is initial portion. The first portion of the green phase that an actuated controller has timed out for vehicles waiting between the detectors and the stop line during the red phase. Minimum period. The shortest time that should be provided for a green interval during any traffic phase. Extendable portion. The portion of the green phase that follow the initial portion to allow for more vehicle arriving between the detector and the stop line during the green phase to go through the intersection. Extension limit. The maximum additional time that can be given to be extendable portion of a phase after actuation on other phase. Unit extension. The minimum time by which a green phase could be increased during the extendable portion after an actuation on the phase. However, the total extendable portion should be not exceed the extension limit. Demand. A request for the right of way by a traffic stream through the controllers. Next is semi-actuated, will be presented by Wan Muhammad Hafiz.
Okay, Assalamualaikum. Can you hear me? Okay, next slide. Okay, so as we know, actuated signal actually we have two types of actuated signal, which is semi-actuated and fully actuated. So for the semi-actuated signal, we only have one detector which is put on the minor stream flow only. So it is applicable primarily to an intersection of a heavy volume, urban or suburban traffic arterial with a relatively lightly traveled minor road. Next slide. So here is the essential operating feature for the controller for the semi-actuated signal. So as stated before, detector are on minor approach only, and then the green signal on the major approach is preset for a minimum period, but it will stay on until the signal is actuated by a minor stream vehicle. If the green signal on the major approach has been on for a period equal to or greater than the preset minimum, the signal will change to red in response to the actuation of the minor stream vehicle. Next, the green signal on the minor... The green signal on the minor stream will then come for at least a period equal to the preset minimum for the stream. This minimum is given by an extendable green for each vehicle arriving up to preset extension limit. The signal on the minor stream then changed to red, and that on the major stream changed to green, and then so on. Okay, next slide. Okay, so for the minor stream, we should set the time for the initial portion, unit extension, maximum green, which is the summation of initial portion and extension limit, and also the change interval. Whereas for the major stream, time should be set for the minimum green and change interval. So if the pedestrian actuator are installed, it is also necessary to set a time for pedestrian clearance. Note that the semi-actuated signal will be set as a pre-time signal if during the peak hour, whereas the vehicle volume at the minor stream is high for that time. So for the minimum green is the summation of initial portion and the unit extension. Okay, next slide. So here is the formula where we use for the unit extension for the detector. So unit extension is equal to x over 0.278 u, whereas the u is for average speed and x is the distance between detector and the stop line. So the unit extension is the time that allow a vehicle detected at the end of the initial portion to arrive at the stop line just as the signal is changing to yellow and to clear the intersection during the change interval. Okay, next slide. But if we desire to provide a unit extension type that allow the vehicle to clear the intersection, we use the unit extension time formula. It is just as the same, whereas the x plus w plus l over 0.278 u, and the w is the width of the cross streak and the l is the length of the vehicle. Next slide. So here is the initial portion formula, hm plus k1, whereas the h is the average headway. In the textbook it says preferably 2 seconds, and is the number of vehicle waiting detector and the stop line. K1 is the starting delay, whereas it is preferably 3.5 seconds stated in the textbook. So this time should be adequate to allow vehicle waiting between stop line and detector during the red phase to clear the intersection. Next slide please.
Sekejap. M tu apa? HM. Formula dia HM plus K1 ni kan? So M ke N situ?
Oh, typo itu N.
Sure?
Sure.
Check balik ya. Check balik
N. It's N. Typo.
Okay, continue.
Okay, for the fully actuated signal, next slide. Fully actuated signal means we have both detector at the both stream. It is suitable for intersection at which large fluctuation of traffic volume occur on all approaches during the day. Maximum and minimum green time are set for each approach. So for this explanation, let's consider a two-phase signal system at intersection below. Next slide. Okay, as you can see from the figure, we have two phase and then we have a direction from 1, 2 and then direction from 3, 4. So if the phase 1 is given the right of way, the green signal will stay on until the minimum green time ends. And an approaching vehicle in the 3, 4 direction actuate one of the detector for phase 2. Then a demand for the right of way in the 3, 4 direction is then registered. If there is no traffic in the 1, 2 direction left, the red signal will come on for phase 1, and then the right of way will be given to the vehicle in the 3, 4 direction. That is, the green indicator will come for phase 2. Next slide. So next, this right of way will be held by phase 2 until at least the minimum green time expire. But if there are no vehicle at the 1, 2 direction at the end of the minimum green time for phase 2, and vehicle are still moving from the direction of 3, 4, then the right of way will be still given to the phase 2 until the maximum green time is reached. So after the maximum green time for phase 2 is reached, right of way will be given to the phase 1, and then the cycle repeat and so on. And then for the we can still using the formula, those three formula to set the time. Okay, next.
Okay, Assalamualaikum and very good morning. So now we are going to focus on the signal timing of arterial routes. So basically in urban areas where two or more intersections are adjacent to each other, the signal should be timed so that when a queue of vehicles is released by receiving the right way at an intersection, these vehicles also will have the right way at the adjacent intersections. Thus, this coordination will definitely reduce the delay experienced by the vehicles on the arterial. And in order to obtain this coordination, all intersections in the system must have the same cycle length. But then in some rare instances, some intersections in the system may have cycle length equal to half or twice the common cycle length. It is usual for a common cycle length to be set with an offset in which the time lapse between the start of the green phases of two adjacent intersections on an arterial that is suitable for the main street. Traffic conditions at a given intersection are also used to determine the appropriate phases of green, red, and yellow times for that intersection. Next slide, please. Okay, so basically there are three methods used to achieve the required coordination, which are, first of all, the simultaneous system, the alternate system, and the progressive system. So here, the speed of progression is also important in determining the cycle length for each of these methods. The speed of progression is basically the speed at which a platoon of vehicles released at an intersection will proceed along the arterial, and it is usually taken as the mean operating speed of the vehicles on the arterial for the specific time of day that being considered. So this speed is represented by the ratio of the distance between the traffic signals and the corresponding travel time. So next slide, please. Okay, so now I'm going to pass the presentation to my friend Akram Shami.
Assalamualaikum and salam sejahtera. Thanks, Iqbal, for allowing me to continue the presentation. In a simultaneous system, all signals along a given strip operate with the same cycle length and display the green indication at the same time. Under this system, all traffic moves at one time, and a short time later, all traffic stops at the nearest signalized intersection to allow cross-road traffic to move. The mathematical relationship between the bank speed, which is in both direction, and signal spacing in a simultaneous system can be described as follows, where U equals to X over 0.278 times C, where X is average spacing for signals in meter, U is progression speed in kilometer per hour, and C is cycle length in unit second. Next, please. With the alternate system, intersections on the arterial are formed into groups of one or more adjacent intersections. The signals are then set such that successive groups of signals are given the right of way alternately. This system is known as the single alternate when the groups are made up of individual signals. That is, when each signal alternates with those immediately adjacent to it. It is also known as the double alternate system when the groups are made up of two adjacent signals, and so on. The speed of progression in the alternate system is given as follows: U equals to N times S over 0.278 times C. The value of N is depend of which type of alternate system that we need to use, where N equals to 2 for the simple alternate system, N equals to 4 for the double alternate system, and N equals to 6 for the triple alternate system. An alternate system is most effective when the intersections are at equal distance from each other. Next slide. From example 8.8, we can observe that how to choose an appropriate alternate system for an urban arterial. In this question, from the given condition, we need to determine whether a single, double, or triple alternate system is preferable for this arterial if the velocity on the arterial is 56 km per hour. Since there is one intersection in another coordinated system, it is necessary to use the cycle length at that intersection, which is C equals to 60 seconds. We also need to use equation 8.20 to determine the progressive speed for the each alternate system. For the single alternate system, we got 18 km per hour and 36 km per hour for the double alternate system. Next. And the mean speed for the triple alternate system is 54 km per hour. Thus, since the mean speed is currently 56 km per hour, the triple alternate system is preferable because this requires a progressive speed that is approximately equal to the existing mean speed. Now, my friend Rukbal will continue the presentation with his part. Thank you.
Okay. Thank you so much. And now we will proceed with the progressive system. So what is actually the progressive system? The progressive system provides for a continuous flow of traffic through all intersections under the system when traffic moves at the speed of progression. The same cycle length is used for all intersections, but the green indication for each succeeding intersection is offset by a given time from that of the preceding intersection, depending on the distance from the preceding intersection and the speed of progression for that section on the street. When the offset and cycle length are fixed, the system is known as the limited or simple progressive system. Meanwhile, when the offset and cycle length can be changed to meet the demands of fluctuating traffic at different times of the day, it is known as the flexible progressive system. Okay, next slide. Okay, going to the design of progressive signal system. The design of a progressive signal system involves the selection of the best cycle length using the criterion that the speed of progression is approximately equal to the mean operating speed of the vehicles on the arterial street. This selection is accomplished by a trial and error procedure, and equation 8.19 from which is the equation from the simultaneous system can be used to obtain a suitable cycle length by using the mean operating speed of the arterial for U and the measured distance between intersections as X. In addition, the required cycle length for each intersection should be computed and compared with that obtained from equation 8.19. And if this cycle length is approximately equal to those obtained for the majority of the intersections, then it can be selected on a trial basis lah. Okay, next slide, please. Okay, there are 6 first steps used in any method, which are, first of all, the collection of adequate data on traffic volumes. Next will be the intersection spacings, the speed limits, the on-street parking, the operating speed, and the street geometrics. Okay, so nowadays, there are also some computer programs that have been developed to cope with several problems associated with progressive signal timing, such as the large variations in distances between intersections, the differences in speeds between traffic streams in opposite directions, the variable speed patterns in different sections of the system, and the requirement of a high level of computational effort. So next slide, please. Okay, with the advent of microcomputers, several programs have been developed that can be used to design an arterial signalized system. One such program is a version of Transit 7F, which is a system that uses a generic algorithm to optimize cycle length, phasing, and also offsets. So Transit 7F can also be used for several intersections along a street or a single intersection with complex or simple characteristics. It provides a time-space diagram screen that gives a graphical representation of signal progression along the major street as shown in the figure attached. So basically, this is the example of surface interface lah. And then the program has been integrated with the highway capacity software, which is the HCS and COSIM, so that candidates of timing plans obtained by Transit 7F can be evaluated. Okay, next slide, please.
Alright, so now we are going to discuss about the freeway RAM control. It is the application of control devices such as traffic signals, signing, and gates to regulate the number of vehicles entering or leaving the freeway in order to achieve some of the operational objectives. The objective is to balance demand and capacity of the freeway in order to maintain optimal freeway operation and prevent operational breakdowns. Next slide. Okay, there are 2 applications of free RAM control, which are entrance RAM and exit RAMs. For the entrance RAMs, it is to regulate the number of vehicles entering the freeway and to reduce the freeway crashes. And for the exit RAMs, it is to reduce safety hazards and congestion and to encourage more traffic to leave the freeway. Next. Alright, so there are 3 methods for controlling freeway entrance ramps: closure, local or isolated metering control, and system-wide or coordinated metering control. Next slide. Okay. So here is the objective of each method. The first one is closure. It is the simplest form of RAM control, but unfortunately, it is the most restrictive. It is seldom used technique except on short-term basis. The second one is local metering control. This method uses condition at a specific RAM to determine the metering rate, and the primary objective is to improve safety at the RAM. The last one is system-wide metering control. The conditions include those at other adjacent RAMs to determine metering rate, and it is more effective than the local control in dealing with capacity reduction. Next slide.
From the method which is the closure, there is type of RAM. First is the permanent closure. A RAM may be closed on a permanent terms or demand. Concrete barriers are recommended. Next is the temporary.
Natalie, tak dengar lah.
Hello.
Slow sangat. Boleh dekatkan sikit dengan speaker. Dengan mic tu.
Clear ke? So continue. Temporary closures. The entrance ramps may be closed temporarily in response to maintenance or construction activities, either on the freeway or the adjacent frontage road or surface street. It is not uncommon for a ramp to be closed by police during management of a downstream incident. Next is the time delay or schedule. Because of extreme recurring downstream capacity deficiencies, ramps may be closed during certain peak period and also open at off-peak times. For both the method, local metering control and also system-wide metering control, there is also the method which is the method of controlling RAM meters. Next. So this is the slide for methods of controlling RAM meters. The first is the system pre-time metering, which refers to a fixed metering rate that is not influenced by current mainline traffic conditions. It is the simplest form of entrance RAM metering, and the basic system consists of a traffic signal with two sections, which is green and red, or three sections, which is green, yellow, red indicator. Next is the traffic responsive metering. It is directly influenced by the mainline and also RAM traffic conditions. It is selected on the basis of real-time measurements of traffic variables, and the basic requirements include a traffic signal, detectors, a RAM control sign, and also a controller. Next. So based on both of the picture, which is the system pre-time metering and also the traffic response metering. For the first is the system pre-time metering. There is also a warning sign which informs motorists that the RAM is being metered, a controller which is actuated by a time clock, and also detectors shown are optional, but when used will enhance the efficient operation of the system. For the next picture, which is traffic response system, there's optional features include, which is the queue detector, which when continuously actuated indicates that the vehicles queued on the ramp may interfere with traffic on the local road. There's also a merging detector, which indicates whether a merging vehicle is still in the merging area, and also a checkout detector, which indicates whether a vehicle uses green interval to proceed to the merging area. Next. So lastly is the method to determine the metering rate. The first is the local traffic responsive. This method uses traffic conditions immediately upstream and also downstream of the metering ramp to determine the metering rate. It is similar to the pre-time system in that it is frequently used as backup when a system-wide traffic algorithm fails. In contrast to the pre-time system, monitoring of traffic conditions along the freeway with loop detector is required. And next is the system-wide traffic responsive, which is used to optimize the flow of traffic along the freeway. The selection of metering for a location influenced by the traffic condition at other ramps within the system or along the corridor. It is necessary for data to be collected from many upstream, downstream ramps, and also from cross-street signal controllers and also the central computer. That's it. Thank you.
Okey, terima kasih kepada kumpulan 6. Ada soalan ke nak tanya kepada kedua-dua kumpulan? Ataupun saya serahkan kepada Dr. Su untuk apa ni? Nak tanya soalan ke, nak wrap up ke dengan kita punya presentation hari ini? Dr. Su, silakan.
Terima kasih Dr. Izzy. Good presentation from both of the groups. Well done. Cuma saya nak apa nama tu? I think it's all covered. Cuma macam nak cakap nak tanya the class, do you really understand what we were talking about? Okay, so basically we were talking about signalized apa nama tu traffic signal kan. So traffic light lah, basically it's traffic light. Okay, and then tadi your friends present, and then if you go apa nama tu through together, ada beberapa apa nama tu, ada beberapa phrase yang you should really understand and kira master lah for this topic. Satu yang phrase tadi tu, so you should know kalau two phase tu macam mana junction dia, macam mana intersection dia yang apa nama tu require two phase apa nama tu signal ataupun three phase, four phase macam tu. And then because basically apa nama tu this apa signal ni untuk provide safe and efficient traffic flow kan. So cumanya satu tadi saya nak stress, both of the groups kalau you perasan kita banyak discuss on left turn kan. So it's left turn kan. Why is it left turn? Sebab kita punya buku teks is in apa nama tu it is the US version kan. So kalau kita dekat sini left turn yang simple punya kan, ada setengah apa nama tu intersection tu, setengah junction tu dekat kita punya left turn tu dia cuma letak apa nama tu sign yang tiga segi tu je kan. Belok kiri jika tiada kenderaan kan. So sepatutnya sebenarnya kalau macam kita punya case dekat Malaysia ni, if you refer to ATJ untuk untuk kita punya traffic signal ni, kita pakai ATJ 13-87. Latest is pindaan 2017 ya. A Guide to Design of Traffic Signal. So sebenarnya yang dekat sini, dekat Malaysia ni, yang critical is the right turn. Betul? If you drive kan, sebab kita sini kita panggil apa? Right hand driver Kita punya driver dekat belah kanan kan. And then kita punya jalan pun kita belah kiri kan. So bila kita nak masuk kanan tu, that is the conflict kan. Because kalau kita nak masuk kanan, kita kena sorry sekejap. Sorry. So untuk itu dalam ATJ ni, if you see dia tak tulis left turn, dia tulis right turn. Okay, so the concept is still the same, but in our case kalau kita design for right turn. Macam dekat section 3 ni, signal operation requirement, so kita ada right turn facing. Macam tadi tu your friends explain about left turn facing kan. So kita pakai right turn facing. So basically the concept is still the same, cumanya the right and left. Right. So you can refer to this ATJ 1387 and then dekat hujung sekali tu, last sekali tu they will have worksheets. Apa nama tu, ada step calculation example juga, and then how you design traffic signal. I think it's good if you can spend some time and refer. Apa lagi ya? I think itu je lah. Just kalau ada apa-apa soalan, sebab kadang-kadang it can be a bit confusing kan, kanan dengan kiri. So you can always ask Dr. IZZI atau you can ask me. Alright. Dan lain tak ada apa kot. I think that's all, Doktor.
Terima kasih Dr. Su. So saya ingat kita berhenti dulu kelas kita untuk hari ini sebab saya nak kena attend satu meeting ni. Dah lambat 10 minit lah sebelum masuk ni. So apalah, kalau ada any questions nanti boleh tanyalah sama ada through WhatsApp group ke ataupun akan kumpul soalan tu and then ask next week macam mana kan. So terima kasih semua. So nanti kita jumpa besok dalam pukul 12 tengah hari for the talk lah. Right, terima kasih. Okay, Assalamualaikum.
Waalaikumsalam. Thank you, Doktor.
Thank you, Doktor.
Terima kasih semua.
Thank you, Doktor.
Sorry.
Thank you, Doktor.
Sorry, keluar dari meeting pula. Terima kasih.